Let me unfreeze. So, first of all, what is reduction? How are we going to tell if something is a reduction? What's that? It gains electrons, so where is the oxidation number going to go, up or down? Is it going to get more positive or more negative? More negative, okay? So, what did you guys come up with for your answer? Anyone get the answer yet? Okay. All right, let's walk through it then. Let's look at A. In this case, our oxygens are going to be the way we're going to deduce the oxidation numbers of the sulfur, right? Because our oxygens are always going to be -2. So right now, we've got -2. Oops, sorry. No. There we go. So this oxygen -2 times 4 gives us -8. But since we are ending up with an overall -2 charge, we only have to balance out 6 of these. So our sulfur here is going to be +6. Here we've got 3 oxygens. That's going to give us -6. This is going to be +6. So there is no reduction here. It's staying the same. Okay? So it's not A. Manganese here, the manganese in the Mn2O3 are manganese. You can also, for something like this, when you have the full compound, you can also do the reverse crisscross. So this is a +3 manganese, and this is a +2 manganese. Okay? Is that right? Yes, because this needs to be, right, because this is going to be -6 from our 3 oxygens. So we need a positive, what? Yeah, sorry, +4, that's what I meant. Yeah, I knew there was something wrong here because the answer is not B. Okay, sorry, thank you. Let me, yes, this is 2 oxygens, so the -2 is going to be +4. Here, we've got 3 oxygens for a -6. That means we have to have a total positive oxidation state of 6. We have 2 manganese atoms here, so we have to divide our total +6 by 2. Each manganese atom is going to have an oxidation state of +3. Okay? You see where I get that? Okay. All right, so +3 to +4 is going up. That is oxidation, right? All right, here we have a compound that you should be able to recognize. What is this? This is hydrogen peroxide. What is true about oxygens in hydrogen peroxide? Or in any peroxide? That's right, it has a -1 oxidation state. So, our hydrogens are always +1 here. In our OH minus, is this a peroxide? Is it in a compound with fluorine? So what's the oxidation state of oxygen? -2. Are we going up or down? Down. So are we oxidizing or reducing? We're reducing. Right. Our oxygen is going from -1 to -2. It's being reduced. Okay. Down here, we can go through this if you want. So our Cr, our chromium here is the thing that could potentially be oxidized or reduced. So we've got 4 oxygens here, so that's -8, except we have an overall -2 charge on the ion, so that makes this a +6. Here we've got 7 oxygens, so that gives us -14, right? And except we only have to account for 12 of those because we've got an overall -2 charge. So we have a +12, but we have 2 chromiums. So that's also going to be a +6. It's not going to change. Okay? So C represents a reduction. Any questions on these? Anything not clear? Okay. All right. We are going to rush through the activity series today and touch on the Winkler titration. This is a really straightforward thing. We're not going to get into the weeds about this because you don't have to. So we're going to talk about what the activity series is. We're going to talk about how you would use it in to figure out whether a reaction is going to happen or not. And then I will pull up, I forgot to put it in here, I'm going to pull up a question from the question bank, because we're going to do some of the questions in your study guide. While you're doing those, I'm going to pull a question bank question in that deals with this. Okay, so the reactivity series or the activity series generally follows the trends in reactivity on the periodic table. Not completely, because there's some complicating factors. You can look it up online. It's one of those tables that exists online. You can look it up in your data booklet. Of course, I can't remember which number it is. Number 25 in your data booklet on page 24 has the activity series. So if you're being asked to do anything with it, you will be referenced. It will be referenced by your data booklet. So that is correct. You only, well, no, there will be paper one questions, but they won't require you to have the activity series. I'll give you an example of that in a few minutes. All right. The idea, though, here is the elements at the top are the most reactive ones, in that in the context of redox, they really, really, really want to give up their electrons. They just, here, take them, please, you know? And then down here, as we go down, we get elements that are less and less and less likely to give up electrons. They become less reactive. If you'll notice, our noble metals, our silver, gold, and platinum, are down at the bottom. The reason that they are so shiny and used for jewelry and stuff like that is that they are not very reactive. They don't tarnish very easily. They don't rust. So they stay shiny for the most part. Silver does tarnish, but this is why your jewelry, your candlesticks, etc., fancy decorations are made out of these metals, because they don't react with the air very much. Not as much as these others do. You'll notice that carbon is in there and hydrogen is in there. The rest of them are metals. So it's usually called the activity series of metals or the reactivity series of metals. But carbon and hydrogen play an important role in here as well. So again, this is starting on page 11 in your study guide. So again, most reactive on the top, least reactive on the bottom. We include carbon and hydrogen for a couple of reasons. Hydrogen is down here. Anything above hydrogen will react with acids to produce hydrogen gas. Remember, we talked about one of the characteristics of acids is that they react with metals to produce hydrogen gas. Only the ones above hydrogen in the activity series will do that. We'll talk about why in a minute. Carbon is in here because carbon is often used, it's a very plentiful element, and it's often used for purifying ores, metal ores. So metals, for the most part, do not exist in their natural state, you know, chunks of lithium or chunks of aluminum. They exist as ores, as combinations with other elements and other metals. And one of the ways we purify them is by using carbon. And so carbon can purify any of these metals down here, but not the ones up top. There are other ways that we use to purify those, particularly electrolysis, which we'll get to tomorrow. I'm not going to go into this. I'm going to leave this slide in here so you can look at it. Basically, reaction with acid, everything above hydrogen in the series is going to react with acid. Anything below it is not going to. So we could pour some HCl, diluted at least, or some diluted HNO3 on some gold and nothing would happen. Okay? And then reaction with air, again, the ones on the bottom are going to either not react with air at all, the oxygen in the air, or they're going to react very slowly. So gold doesn't react at all. Silver will react very slowly to make tarnish. Reacting with water, also very strong reaction with water at the top. Remember the potassium blowing up when it hit the water? Yeah, that's a very strong reaction with water. Down here, they don't really react with water. And then the same thing with extraction, based on extraction from ores. Hard to extract at the top, easier to extract at the bottom. Down here at the bottom, gold is actually found as chunks or flakes of gold just sitting in the earth. So if you think about, panning for gold and the gold rush and all that, it was just sitting there, not mixed with anything because it's really not reactive. Okay, so there's a type of reaction called a displacement or replacement reaction, sometimes specifically called a single displacement or single replacement reaction. You may remember those terms from honors chemistry. This is where a more reactive metal, we're going to talk about the metal version first, displaces the less reactive metal. So we've got a solution of one thing, and we stick a more reactive metal in it. That more reactive metal is going to kick out the less reactive metal, and that is basically what we did in our enthalpy lab when we put the zinc in with the copper sulfate. Zinc is above copper on the activity series. So zinc wants to lose electrons more than copper does. And this is in your, this part is straight from your study guide. Okay, so we've got zinc, solid zinc, being mixed with our aqueous copper sulfate. That was that blue solution. When we put that in, we had some heat generated because of this reaction. Eventually, if we had dilute enough copper sulfate, we would actually lose the blue color because all of the copper would come out of solution and all of the zinc would go into the solution. Okay, if we had enough zinc. So what's happening is right now, the copper that we start with as a reactant is a 2+ ion hanging out with the sulfate in solution. Really hanging out with the water molecules in the solution. The zinc comes in and says, nuh-uh, I want to be an ion more than you want to be an ion. So here, take my electrons. I don't want these electrons, you have them. And copper says, okay, I don't mind having these electrons. I don't mind hanging out as a neutral element. That's fine with me. And zinc comes in and replaces it as the ion in the ionic compound. So we start, these reactions always start out with a single element coming in and kicking out something else, so that our copper comes out of the solution as solid copper, and we had that precipitate in our solutions. It was hard to tell because we had excess zinc in there, but the zinc will now become a 2+ ion. So it's a redox reaction because we're moving the electrons from the zinc to the copper. So which of these is being reduced? The zinc or the copper? The copper. We're going from +2 to 0, right? Our zinc is going from 0 to +2, so our zinc is being oxidized. What is the oxidizing agent? Yes. Excellent. So whatever is being reduced, that reactant is the oxidizing agent. So copper is reduced in this reaction, so the copper sulfate is considered our oxidizing agent. Yep, zinc is a reducing agent. The higher you are in the activity series, the stronger reducing agent you are. Okay. So this is not in your study guide, but this table is an example of what you can do to determine the activity series of a set of metals. There are lots of ways you can test it. One is to just put a bunch of ions in different solutions and then test with the different metals. Obviously, copper in a copper solution is not going to do much unless we stick some electricity in there. If we put copper in a solution of iron, it will not do anything because iron is above copper. Remember, copper is pretty low It's down there almost with gold and silver and platinum. All right, it's not going to do anything to magnesium. It's not going to do anything to zinc because it is lower on the activity series, and so it doesn't want to be an ion as much as these guys do. Iron, if we have a solution of copper and we stick a piece of iron in it, we will have a reaction where the iron will come in and kick out the copper, take over as an ion, and boot out the copper as a neutral precipitate. Okay? Magnesium can boot out everything. Obviously, it doesn't do anything in a solution of its own ions. But magnesium can boot out any of these, copper, iron, or zinc. Zinc can boot out copper or iron, but not magnesium. So if we were to take results like this and create a table, who would be at the top of our reactivity series? Copper, iron, magnesium, or zinc? Based on these data. Yeah. Yeah, so we'd have magnesium at the top because it can replace everything else. What would be next in the series? Yeah, Bubba? Zinc, yep. Because zinc can take on copper or iron. And then we would have iron, and then we would have copper at the bottom. And we could look up an activity series table and find that that is, in fact, the order. So the activity series, I like to think of it as a tournament ranking in which there are no upsets. There are never any upsets. So it's like if everything in March Madness went to seed, it would be like the activity series, okay? All right, so on page 12, you have some reactions. This is where this is similar to what they were asking you to do in the acid-base packet to predict the products. Now, it's possible that your products might be no reaction, okay? If the single element is not high enough to kick out the ion, then there will not be a reaction, and those two substances will just sit there forever in a beaker doing nothing, okay? So the two steps that you have to take to answer these are, say, is the single element higher on the series? If it is, then what is it going to form when it reacts with the other substance? So looking at number 1, potassium, you should have the activity series on one of those pages. Potassium, you can see, is pretty high on the activity series, right? Lead is pretty low, just above hydrogen. It's not all the way down with the noble metals, but it's fairly low. So this is, in fact, going to be able to kick out the lead. So we are going to have this reaction. So that's going to leave us with one of our products as the lead metal by itself, because that's what's getting kicked out. And that's going to be a neutral lead. So that's just going to be solid lead, going to hang out at the bottom of the beaker. And then we're going to make a compound between potassium and nitrate. This is where you have to remember the charges and make sure that this is balanced, or do whatever you need to do with the subscripts to make it, to balance it out. What's the charge on a potassium ion? +1. What's the charge on a nitrate ion? -1. Okay, so this is already balanced. I didn't have to write that. In fact, you shouldn't write it in the final version, so I'm just going to say it's just KNO3, okay? So you don't, I'm just saying if this wasn't correctly balanced, say this was magnesium, we need to give ourselves 2 nitrates to balance out the +2 magnesium, right? But here we don't have to, so it's just, I'm actually going to erase this, and your answer would just be Pb solid and KNO3, which would presumably be aqueous, the ionic compound dissolved in the water, okay? So practice a couple more of these. So what's your answer going to be for number 2? Yes, this would be, oops. We just say no reaction. Because magnesium is lower than cesium. What about number 3? No reaction. What about number 4? How about number 4? Also no reaction. Okay, in all of these cases, the single element is below the thing that is already an ion. It is not going to be able to kick it out. The last one, though, you will have a reaction because silver is just below copper on the series. So our silver is going to come in, our copper is going to come in and kick out the silver. And then this is where there are multiple possible answers to number 5. Why is that? Yeah. Yes, copper can have different charges, different oxidation states. As a transition metal, it usually is either +1 or +2. So you would, in answering this, they probably wouldn't put that on a quiz. See, lead is in the same boat, but in this case, in this problem, it wouldn't matter because the lead is going to be by itself. It's not making an ion. Here, where our copper is forming an ion, it is very unlikely that they would put that as a question. But you could, a possible answer would be Ag solid plus CuNO3 aqueous, or it could be plus CuNO3 2 aqueous if this was a +2 copper. And either one of these would have to be acceptable because you don't know a priori which one it's going to be. Okay? So again, that's probably not going to show up on the test. I think they're smart enough to not do that, or to give you some clue as to which one it would be. Maybe you would see that in the multiple choice where only one of these would be in the answer choices. Speaking of multiple choice, this is sorry, this is still a little hard to read. This is a question from the question bank. It says, metal X is added to Y sulfate solution, or metal X is added to Z sulfate solution. And here's what happens. So rank X, Y, and Z in order of increasing reactivity. This is all you get, but that's all you need. And you can go through this as a process. Roger, what's the answer? Yeah, it's B. Here's why. X cannot replace Z. Okay? That means Z has to be above X. Okay? Going for decreasing reactivity. Okay? So now we have to figure out where Y goes. Well, X can replace Y. So Y has to be below X. So we didn't even have to do the reaction between Z and Y because we already know if Y is below X, then it has to be below Z. Okay? So Y is less than X is less than Z. And that's the answer choice. Okay? So that is, I've seen several questions like this as a very possible question that would be in the multiple choice form. All right, moving on. There is one more type of displacement reaction that you might be asked about. And that is not with the metals, but with our group 17 elements, the halogens. Because they are also very reactive, just on the other side of the table, right? They really, really want to lose electrons. So, gain electrons. Sorry, said that backwards. So our metals on the other side of the table, on the left side of the table, really, really want to lose electrons. These guys really, really want to gain electrons, but they also have a hierarchy of how badly they want to gain electrons. Fluorine desperately wants electrons. And it goes down from there. It just goes down the table. Okay? So if you remember that fluorine is our most reactive nonmetal up in that corner, then you can, get everything else from there. Okay? So reactivity decreases down the group, and their ability to oxidize, to be an oxidizing agent, increases as we go up the group. And so, for example, we might have some chlorine as our single element being added to some potassium bromide. We're not kicking out the potassium, we're kicking out the bromine. The negative ion's going to kick out the nonmetal's going to kick out the nonmetal, right? So when we're talking about displacement reactions with the metals, it's basically whatever the single element is coming in, it's going to kick out the thing that's like itself. So in this case, chlorine's going to come in, kick out the bromine. Bromine's going to be by itself, and the chlorine and the potassium are going to make a compound together. Okay? And you can write this. This is the full molecular equation. Here is the ionic equation for that. And on page 13, you have, I just put a couple of these predictions whether the reaction will occur. So notice these don't have compounds, but you can imagine that the ion in the reactants is in a compound, right? So that I minus could be in a compound Ki, it could be in, who knows? Could be a compound with anything. It doesn't matter. What matters is that the iodine is already an ion. And the question is, can chlorine come in and kick it out? So is this reaction going to occur where chlorine becomes an ion and leaves iodine on its own? Is reaction number 1 going to occur? Chlorine kicking out iodine. Yes. Chlorine is higher up than iodine, so it wants to be an ion more than iodine does. So it's going to take electrons from the iodines, for those extra electrons that are currently sitting on the iodide ions. It's going to take them for itself, leave the iodine as a neutral compound. And so that means that iodine can't come in and kick out chlorine, so this is a no. Okay? The same concept, exactly the same, and even easier to remember. You don't even need a table for it because chlorine's on top. And that's all you need to remember. Okay. All right. Last thing that I want to talk about today is redox titrations, which we have done with the pool water. Remember when we tested the chlorine in pool? That was a redox titration. Okay? It's very similar to an acid-base titration. You can use measures of electrical current. You can use an electrode measuring current or electrical potential to figure out the endpoint of the titration, but you can also use an indicator, and it's going to be a compound, usually some kind of transition metal complex. The transition metals often will change color based on their oxidation state and what they are complexed with. And so ferroin is one that we were going to use with BABA, and we still may use it after the test to just demo that reaction. This is something that is blue in the oxidized state. When electrons are added to it, it is reduced and it turns red. All right, so it's the same kind of thing as the phenolphthalein or the universal indicator in terms of changing color at a certain point in the reaction. This is an example of what that looks like from Max's IA last year. So he was doing a redox titration and started out with this red indicator, titrated until it turned sort of a pale yellow, and then added starch. Starch turns blue in the context of iodine. So the changing state of the iodine made it able to complex with the starch to make that blue color. And then as the titration continued, it started getting clearer and clearer until we ended up with a clear white solution. All right, so that's a very common, just an example of the color changes that you would see. This is used in the specific example that IB likes to talk about in this thing called the Winkler method, which is what Nick did for his IA. So it's important, they like to bring in the environmental aspects like the acid rain stuff from the acid base. It's important because dissolved oxygen is dependent on a lot of things, including pH, and you have to have enough oxygen dissolved in the water for the marine life to be able to live and to be able to thrive, okay? So it's a very common thing to test the water for the oxygen levels. It can also be used to test this thing called biological oxygen demand, which is basically how much has the oxygen changed. If we take a sample of water and we let it sit for a while, how much does the level of the oxygen change? How much is being used up by organisms in the water, microorganisms? Okay, so that's another common thing that you get in the environmental sciences. If you're taking AP Environmental next year, you might want to do something with Winkler method for your, IB. You might want to do something with the Winkler method for your IA, because you've done titrations, and I'm happy to help you with it. Okay, so there's 3 steps to the method, and this starts. They just go straight to the Winkler method on your study guide, so pages 14 and 15 is what we're looking at here. There's 3 steps. First, we take some manganese and we oxidize it, and that creates this precipitate. The details are not important. If they are asking you to use this, they will give you the equations. Okay? So then we have a bunch of manganese oxide, and we react that with some potassium iodide. So now we're adding our iodine ions, and those are going to get oxidized by the manganese to pure iodine. Okay? And that is where we add the starch, and we start looking at the concentration of I2 in the solution as a way of determining how much oxygen we originally had in the solution. They're actually 1 to 2, so if we start off, we've got 1 oxygen making 2 for every 2 manganese oxides, and then 1 manganese oxide making 1 iodine. So it's a 1 to 2 and then a 1 to 1, okay? And then the last step is the titration with the sodium thiosulfate, and that is going to then reduce the iodine back into ionic form, and that's going to make that blue color go away, because it will no longer be hanging out with the starch, making that blue color. So this, you'll see, 2 is 2 to 1 here. So what we end up with the total sequence, we end up with, for every mole of dissolved oxygen, we use 4 moles of thiosulfate to titrate it. So if you want to memorize anything about the Winkler method, it would be this ratio, the 1 to 4 of oxygen to thiosulfate. I don't think it's, you can also just follow it through the reactions, which again, they will give you if they ask questions about this. So in your study guide, on page 15, there are some example questions. The first one says, we have these 2 samples of river water collected. One is tested immediately for dissolved oxygen, and the other one is stored to be tested after 5 days. So this is a situation where they're testing dissolved oxygen at once, and then later, and the difference between them is going to tell us about the biological oxygen demand of the organisms that are in that water sample. All right, so we're just looking at the day 0. Immediately after, it tells us that we have a certain volume of a certain concentration of sodium thiosulfate that was required to react with the I2 that was produced. Okay? And it says calculate the dissolved oxygen content of the water. So here we've got a volume and a concentration, and then we're going to have a mole to mole ratio of 1 mole oxygen to 4 moles thiosulfate ratio that can help us take us from moles of sodium thiosulfate to moles of oxygen. Okay? So this is where you've got your C equals N over V, right? Your concentration is equal to the moles over the volume. And so we have 0.02 moles per liter of sodium thiosulfate. So that's our C. Our volume is 15.2 milliliters, but we have to put this in liters because of this. So we've got our number of moles over our volume, which is going to be 0.01520. You see where I'm getting that? So then we just solve for N. That tells us the moles of sodium thiosulfate. So then I take my N times moles Na2 is 203. That's going to be a 4 moles to 1 mole of O2 in the reaction, and that gives us the moles of oxygen. And then we take that, that's our new N, we take that, divide by our volume to get our concentration of oxygen. All right, we got through everything I wanted to get through today. That's very exciting. Any questions? Yes. So, so the sheet that I put out is optional practice problems for the redox balancing. I will post a key, and I'm happy to answer questions about that if you are working on them right now, as soon as I stop this recording. Which